see the antiderivative of minus 5 was minus 5u. The antiderivative of 5e to the u was 5e to the u. Does that make sense? What's that work out to? Minus 5 times minus 6 plus 5 e to the minus 6 minus, parentheses, minus 5 times 0 plus 5 times e to the 0. So that's like minus 30. Of course, 5 times 0 is 0, but this is, oh, wait a minute, this is not minus 30, this is 30. Yeah, 30, and this is minus 5. So we get 25 plus 5e to the minus 6. Oh, the 5, that's the 10 over minus 2. I just brought this minus 2 over there, and uh, 5e to the 0, oh, 5 times 0 is 0, but 5e to the 0 is 5. We had 30 minus 5 was 25. See, this is 30, but this is 5. But it's subtracted because of the... It's good? I seem to have worked your problem 148. Sorry. Is it okay? You'll forgive me? Okay. Let's do another. Example 5. Actually, if you don't mind, I'm going to erase and start from the corner. Is that fine? Let me pick on a problem that is a little bit more challenging than the ones we've worked so far, because it requires a little bit of algebra. Integral of x square root of x plus, well, let's say 2x plus 3 dx. So Myron, what do you think I should make u equal to for this problem? Yeah, but, well, u equals to x is, I could just like categorically say u equals to x is never worth it. Because what happens when you make u equal to x is you get the same formula back again with u instead of x. So that's like...
I do have a question. Can I choose between 2x or 3?
Well, you could, I mean, 2x plus 3 is a good choice. I would think that's a fine choice. Make that u. Sure. So I suggest that. Let's make that u. Now, if u is equal to 2x plus 3, then du dx is equal to 2, right? So dx is equal to du over 2, right? So with that substitution, we've got the integral of x square root of u du over 2. Now, what do you do when you make a substitution like this and you've got an x left over? Do you just ignore it? Do you hope that it doesn't matter and you're going to get partial credit? I mean, no, you should face the fact that there's something to do here. In order to be successful at the substitution, then, we need to be able to change that x to a u. How do I do that? what is x in terms of u? I mean, I would focus your attention on this equation right here, right? This is the relation of x to u. So solve that for x. What do we get? X equals, yeah, 3 halves. How about u minus 3? Oh, you had a 3 halves. There's the 3 halves in there, you're right. So subtract 3 to the other side and then divide by 2, right?
Yeah, I thought it was all for X.
Okay. We're good now? So this is x. X is u minus 3 over 2. And now I plug that in. I've got 1/2 times u minus 3 square root of u. And then I've still got my du over 2 here, right? So let me just clean that up a bit. That's 1/4 integral of what's u times square root of u? That's u to the 3 halves minus 3 times u to the 1/2. So the 1/4, I took both of these characters and I put them out here. And then I've got u times square root of u, that's u to the 3 halves. And I've got minus 3 times square root of u, which is just u to the 1/2. And the reason I'm writing it this way is so that I can go back and use the power rule in my head, you know? So I have to take 3 halves, add 1, and divide by that. So I've got 1/4, 2/5 u to the 5 halves minus 3 times 2/3 u to the 3 halves. Plus a constant. So cleaning things up a bit here, I've got 2/10 times 2x plus 3 to the 5 halves minus twice 2x plus 3 to the 3 halves plus a constant. Oh, that's a good question. Where did that 2/10 come from? The answer is, well, I think we're not, I mean, I'm human, I think is the real answer. The answer is that's wrong. 4 times 5 is what? 4 times 5 is 20. 2 over 20 is what? 2 over 20 is 1/10, right? My bad. Yeah. Let's see here. Let's do another example. This one's going to be a little bit different. In fact, this is a foreshadowing of a future lecture. There are other problems which we'll be able to do, but strictly speaking, this is not exactly a u-substitution problem. Like, how are you going to integrate cosine squared? So a problem like this, we have to use other things we know. So what we know about cosine squared is that's 1/2 1 plus cosine 2 theta. Remember that from trigonometry? Well, you might not, but we'll talk more about, we will review more trigonometry next week, okay? Because we all need to review trigonometry. But that's a trigonometric identity. And see, once you have that, then, well, this is integral of, you know, 1/2 d theta plus the integral, plus 1/2 the integral of cosine 2 theta d theta. Now the d theta over 2, well, that we can just straight integrate. That's theta over 2, right? The integral of this piece just gives me theta over 2. But how about the integral of cosine 2 theta d theta? How can we integrate that? What do we want to make a u equal to there? What u substitution should we use for that? There's really only one choice that's kind of like, how about the u equals to what? I heard a 2 theta. Uh-huh. That would be cosine of u, right? So if u is 2 theta, that makes du d theta equal to 2, of course. So d theta is du over 2, right? So we get plus 1/2 integral of cosine of u times du over 2, right? So that's theta over 2 plus 1/4. What's the integral of cosine? Sine, right? Sine of u plus a constant. But then before we're done, what are we going to do? We change back to the original variable, right? So this is theta over 2 plus 1/4 sine of 2 theta plus a constant. So we'll do more of this sort of thing when we talk about integrals of trig functions, all right? There are u substitution problems which also involve trigonometric identities. This we'll spend like a whole day on next week, or at least half hour or something like that. I don't know, 40 minutes, whatever. Let me show you another example. Well, I'm going to erase. Can I erase this? It's kind of in my way now. You good? You good, Taylor? You fine? Okay. Cool. Example 7. Suppose we're faced with the integral of 1 over the square root of x times 1 over 1 plus x squared dx. Ooh, not x squared. I want to actually put an x there. Well, that's the square root of x, though. You got to somehow take care of that, right? Hey, example 8. Integral of, let's say, cosine of x dx over 1 plus sine squared x. Well, but if you make u equal to cosine, then you still got to, I mean, you have to face the sign downstairs. Like, I'll help you guys out. So if we make u equal to sine x here, good things will happen. If u is sine, right? So u substitution it's got 2 prongs, right? Like, one thing is you got to think about the substitution of the integrand, but the other thing is you have to think about how are you taking care of the du. Both of these things have to come together for it to work. right? You can't just think about u and you can't just think about du. You have to think about them together. They're a package deal. So this is du if that's u, is the thing that makes this nice, right? So this is du, and that is 1 plus u squared. So anytime you see if you see something like 1 over something plus a square, you should be thinking about arctangent as your target integral. See, because the integral of this is inverse tangent of u. Yeah. And so that, going back to the original variable, is inverse tangent of sine of x plus a constant. Now that I've done example 8, think back on example 7 now. I'll write it. I'll make another step for you guys. This is integral of 1 over square root of x, 1 over 1 plus the square root of x squared because I want you to see that you can think of that as 1 plus something squared. Which means maybe we can use an arctangent. We can, yeah. Oh, I thought you had a, u equal what? What do you guys think? What's the derivative of the square root function? 1 over 2 square root of x, right? Look, you've got this and this together will make a du. Right? So if we make u equal to the square root of x here, then du dx is 1 over twice square root of x. I'll solve for dx this time just to be different. Dx is, what is it? 2 square root of x du. So I've got integral of 1 over the square root of x, 1 over 1 plus u squared. Dx was 2 square root of x dx, right? So these guys cancel. And we're left with the integral of 2, that was supposed to be du. 2 du over 1 plus u squared. Hooray. So that's twice the inverse tangent of u. Which is twice the inverse tangent of the square root of x plus a constant. Yes, our goal, exactly, this is the thing, is our goal is to use what we know. So what do we know? We have this list of like 20 elementary integrals. Sine, cosine, exponential, the inverse functions, right? Cosh, the sinh, powers, lots of things like this. And our goal is to make a substitution so that our given integral, when we change it to the u, shifts back to one of those basic integrals so we can do it. Like that's u substitution. That's the u substitution, yeah. One last example, this will be it for today. Example 9. What if we had the integral of x plus 2 oh, that's not what I want. Sorry. Integral of x squared over 1 plus x cubed dx. So this is not an arctangent one because there's no nice way to make the denominator become like 1 plus something squared. I mean, it would have to be 1 plus the 3/2 power squared, but then the 3/2 power is not anything related to the x squared up top, so like it's not going to work. So as a generic point of something to try, if I have a u-substitution problem, and I've got kind of a slightly ugly denominator, a lot of times a good choice is to make the denominator the u. Oftentimes this is helpful. So I will try u equals to 1 plus x cubed. Then du dx. Well, du is 3x squared dx. So that makes dx equal to du over 3x squared. So we've got integral of x squared, this is u, and what's the dx? Well, the dx is du over 3x squared. So it was a good choice. The x's cancel out. We're left with the integral of 1/3 du over u. So this is that natural log you wanted me to do a couple examples ago, Shadrach. And there it is. So 1/3 natural log absolute value of u plus a constant. But here u is 1 plus x cubed. So we go 1/3 natural log absolute value of 1 plus x cubed plus a constant. And I would just like to point out that the u-substitution is non-trivial. Like what it's doing for us is pretty neat. If I'd asked you guys a week ago to tell me what function you differentiate to get back cosine of 1 plus 1 cosine over 1 plus 1 plus sine x squared, sine squared of x, I don't think you guys would have been like, oh, inverse tangent of sine x. Right? But we can find our way to that guess using this technique of u-substitution. It gives us a way to bootstrap our way up from like, basic results to slightly more complicated results. And I think it's pretty neat. But anyway, have a good weekend, you guys. Do email me if you're working on your homework and get stuck on something. I do try to help.